Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we have a problem. Today we're going to talk about something called intermolecular forces. This actually makes sense. Intermolecular, that's molecule. Inter means between. So if you play intercollegiate athletics, you play people on another team, like the University of Colorado plays the University of Texas. So between molecules, what does that mean? Well, it turns out there are 3 types of intermolecular forces, and it's going to be better to label them and then discuss them. All right, so the 3 are So as you look at this diagram, we want to talk about the fact that we're dealing with intermolecular. So if we look at a molecule, we ask a question, is it nonpolar or is it polar? If it's nonpolar, it's held together by what's called a London dispersion force. That's an LDF. That's how I like to abbreviate that. We also could have a hydrogen bond. Now, this is actually a bit of a misnomer. It's not a bond. It's a force, but we call it a bond. That's crazy, you know. And then we have something called a dipole force. Now, let's take a brief moment and talk about this word molecule. What is a molecule? Now, this is in contrast with, like, say, salt. So water, as you know, is H2O. But what's really going on, as you recall, when we draw the Lewis structure, which we've drawn before, that's a water molecule. That means there is just one of these. So if I have a cup of water, I have millions and billions and trillions of one O and 2 H's. Very different than if I have salt, right? If I have salt, if you recall, it makes a crystal lattice. It's an Na connected to a Cl, connected to an Na, connected to a Cl, Na to Cl to Cl, etc. And it goes on for this infinite, not infinite, but bazillions of atoms all connected together. But with water, it's a water, just an H2O. That's it. That's what a molecule is. It's an individual sort of chunk. Also with molecules, make sure you know this, they are always covalent. You can't have a molecule of an ionic compound. Molecules only work with covalent compounds. Like water, H and O are both nonmetals, so it's molecular. Okay? But the question we're asking is what holds water to water? Not what holds the H to the O. That's a covalent bond, a single covalent bond with 2 electrons shared between 2 atoms. We're talking about what holds a water to a water. So let's start here with the hydrogen bond. I think it's the easiest to understand. So we're going to draw this. Important that you draw this. So I'm going to draw H, OH. Draw the Lewis structure. And I'm going to draw another water molecule. How about H or OHH? Notice I'm drawing it in the bent shape because that is the correct shape of the molecule. So what we're actually talking about is we're talking about the force that attracts this water molecule to this water molecule, the dashed line, if you will. Okay, so what's going on here, and this is important to diagram this. Remember, what causes everything to attract to everything else is that positive things are attracted to negative things. And if you recall, if we were to draw the arrow, this is the plus in, this is the minus in, that's the plus in, that's the minus in, and this is the, we do the same thing here. Or if you think about it another way, what I've got going on is the oxygen has a negative charge. And actually we use a little symbol here, slightly negative, or I could say slightly positive. The hydrogen is slightly positive, the oxygen is slightly negative, and so because the more electronegative it gets, the more positive, or the more negative side. So if this is negative and this is positive, they're attracted to each other. So it's because they're polar, there's a positive end and a negative end that causes them to attract to each other. Now, hydrogen bond, by the way, is only going to happen in one of 3 cases. You have to have hydrogen bond, right? Plus F, O, or N, fluorine, oxygen, or nitrogen. There was an old movie years ago, it'll date me, when I was in high school, it was called E.T. And you know what E.T. did famously? He said, E.T. phone home. Phone home, F-O-N. It's because these are the most electronegative atoms. It actually makes this stronger. If we're looking at a scale of 0 to 100, this is a strength of 5. Okay? The dipole force is very similar to the hydrogen bond in the way it works, but it's weaker, and it doesn't have H plus F, O, or N. We could have, for example, in NF3, so draw this again also in your notes. I'm going to draw N, F, that's an F. F, that would be a pyramidal structure, and I want to connect it to another NF3, so I'm going to go NF, remember it's this pyramidal structure, F, F. They would have extra electrons around here, etc. I'm not drawing it completely, but I'm getting the right structure. All right, I'll draw it. But what's going on here is, again, we're talking about the bond between NF3 and NF3. It's this dashed line. That is the dipole force. And again, this is going to have a slightly positive charge. Fluorine being the most electronegative atom is going to be the most negative charge, so this negative here is attracted to this positive. So that's called a dipole force. When you have two polar molecules, because they have a positive end and a negative end, that allows them to connect to each other. Make sense? So that's for polar. The one that's the trickiest is always the nonpolars, because they don't have positive ends and negative ends. So I could, for example, I could have CO2. Now, CO2, as you might recall, is a gas. There's some CO2. I'm breathing out right now, right? Carbon dioxide has this linear triatomic structure. And the question is what holds carbon dioxide to carbon dioxide? Again, there's some bonds. You can make them connect. You've probably played around with dry ice. Dry ice is solid carbon dioxide. And so what's going to cause this to happen? Now, jot this word down, or this two words, I guess, this. The word instantaneous dipole. And what's going on here, and this is going to be a little tricky to understand, but since electrons are constantly moving, the electrons here might move over here for just a second, which is going to give this side here just a little bit more, this side a little bit more negative, and this side a little bit more positive. And then maybe some of these electrons are, actually it'd be the other way around, right here. Some of these electrons, these top ones, move over here just for a second because they're always jumping around, which is going to make this side negative and this side positive. So what happens is that because electrons are constantly moving, this is somewhat sort of similar to metallic bonds, but they're moving just in the atom in fixed locations. There's a positive and a negative, which allows them to attract to each other and connect. Now this leads us to a very interesting thing about nonpolar molecules, because nonpolar molecules are interesting because, you know, water boils at 100 degrees, but there are some solid things that are nonpolar. Okay, so think for example candle wax. Candle wax is nonpolar, and it's a big molecule. I'm not going to draw the whole thing, but actually I'll just do 8. 8 is actually a liquid you are familiar with. These are 8 carbons, and 8 carbons with branching hydrogens off of each of them. I'm not going to draw all of them, but etc. And the same is true here on this bad boy right here. This is octane. This is the chemical that goes and makes your car drive, unless you have an electric car. It's gasoline, right? And it branches off anyways. The point here, though, is this is a big molecule. And what's going on is, again, there's lots of instantaneous dipoles, and so there's like dashed lines between here. But you see the difference between this molecule and this molecule. This is big, this is small. And honestly, every substance does London dispersion forces, all right, the LDF forces. And because even in the water, these electrons are moving around creating these things, but the hydrogen bond is so strong it just takes it out. But when we're dealing with a big molecule like octane, actually that's not that big, it's just biggish. Because you have so many jumping electrons, there's lots of little forces. You might think of it like thread. Each London dispersion force is a super weak thread, and then what happens if you put lots of threads together, you can make a rope. And so the bigger the molecule, the higher the London dispersion forces, or the more London dispersion forces. Each London force is just really weak. But if you have enough weak things added up, they can make something strong. Now I want you to sketch out this chart. Kind of a complex chart, but I'll explain it. So the point of this chart is to help us know which things hold together stronger, the ones that have the strongest bonds/forces. Now, let me distinguish between these words bonding and forces. There's 3 kinds of bonds: ionic, metal to nonmetal; metallic, metal to metal; covalent, nonmetal to nonmetal. Okay? I'm going to talk about this thing in a second over here. But in a covalent bond, between the molecules, we have the IMF, the intermolecular forces. right? And the forces are devised by polarity, polar and nonpolar, London forces, hydrogen bonds, dipole. This chart is what we just copied down a few minutes ago. And before we get into too much detail, let's talk about the numbers. The higher the number, the higher the melting point, the higher the boiling point, the stronger that substance holds itself together. And let's talk about this one because we've never learned about these. Covalent network solids are some of the coolest things like in the universe. These are things that are all covalent bonds. Because if you think of a water molecule, which is a hydrogen bonded down here, it is, when we boil it, we don't break the HO bond, right? We've got HOH, HOH. It's this hydrogen bond that you break when you boil it. You don't break the covalent bond. But in a network solid, it's all covalent bonds. The classic example of that is a diamond. A diamond, you can see the structure right here. A diamond is a monstrous 1 megamolecule that is covalent, 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 covalent. There's no intermolecular forces. There's two other big examples we'll talk about. There's silicon carbide and also silicon dioxide. It's just very few chemicals that do this. This is quartz, like sand. Most sands is that. Silicon carbide is another cool thing. These are the high, you can boil a diamond or you can boil quartz, but it's going to be crazy high. The strongest of all substances. This is 100. All right, and these are still quite strong at 15. By the way, no, they're both 15. It's really hard to tell if salt is higher than iron or something like that. You have to look up on a table. But then here we jump to a whole new category. We've got hydrogen bonded, dipoles, and London forces. Notice the numbers, 5, 1, and 0.1, very, very small. Because the kinds of questions you're going to be asked to deal with, let's say I've got 4 substances. I've got salt, as in sodium chloride. I've got water. I've got a diamond. And I've got methane, or CH4. And I'd ask you to rank them from highest to lowest melting point. So high to low melting point, MP standing for melting point. So which one would melt at the highest temperature? What you have to do is you have to figure out where on this table that they fit. So salt, you find salt is a Na to Cl, metal to non-metal. So he is right here, so you'd put a 15 next to him. So he's pretty high, right? Water, and I've already given this away and you probably got this memorized. Water is a covalent, metal or non-metal to non-metal. Covalent, it's polar. It's polar because we've drawn the Lewis structure, and because it's got, remember, it's H plus FO or N, so you've got hydrogen and oxygen together. That makes water a hydrogen bond, so he is a 5. You see what I do is I need to assign a number, and then I can rank them. It's easy. Diamond, easy, right? He's 100. All right, so big boy here. He's the big boy. And then methane, CH4 is methane. You'd have to draw the structure, by the way, non-metal to non-metal, so it's covalent. Polarity, when you draw that, all right, I'm going to just draw it because I know this. So you're going to have to, you have to draw this for yourself. This is a tetrahedral shape, and it's nonpolar. So this is a London force, so it's 0.1. So if I were to put them from high to low, diamond would be number 1, right? Salt would be number 2. Number 3 would be water, and number 4 would be methane. So you can rank them based upon knowing what type of a chemical they are. If I, by the way, substitute salt and I put iron, the symbol Fe, you would still be a 15. If I won't give you one where you have to compare iron to salt because it's hard to tell by just looking at them. They can be figured out by looking up on a table. But yeah, intermolecular forces and bonding, fascinating subject because it tells how things stick together and what makes everything up. Houston, we don't have a problem. We'll see you in class.